Welcome to Notes 2.3. Today we're going to be doing pretty much the same thing that we were doing yesterday, but instead of square roots, we're going to do nth roots, which the n just stands for number. So we're going to be looking at cube roots, fourth roots, and fifth roots today. So we're going to start with the warm-up, make a list of perfect cubes, fourths, and fifths. So we did this yesterday with squares, and today we're doing the same thing, but cubes, fourths, and fifths. So cubes, it's when you multiply a number times itself 3 times. So you can see like 8 comes from doing 2 to the third power. That means 2 times 2 times 2. And 27 comes from 3 times 3 times 3, and so on. So that's what all of these numbers are, and I wanted to show you again how you can get these in your calculator if you forget how to find them. So cubes means you are doing x cubed, fourths is x to the fourth, and fifths is x to the fifth. So if I go to my calculator, y equals, and type in x squared, or sorry, x cubed, so I have to hit the caret button to get the exponent, and go second graph, you can see starting at 1, all of your y values, those are your perfect cubes. So 343, for example, is 7 times 7 times 7. And 1,331, that's 11 times 11 times 11, and so on. So I can do this for the fourth roots, so I can do x to the fourth, second graph, and starting at x equals 1, I get my perfect fourths. So for example, 20,736, that's 12 times 12 times 12 times 12, because we have the fourth power. And then same thing, x to the fifth. So these are all of my perfect fifths. So 3,125, for example, is 5 times 5 times 5 times 5 times 5, because it's 5 times. It's 5 to the fifth power. So just like we were using the perfect squares for simplifying square roots, we're going to be using these numbers to simplify our nth roots. So just a review on square roots. The square root of 9, well, that equals 3, because 3 times 3 is 9. The square root of x squared, that was x. And the square root of x to the fifth, remember square root, there's an imaginary 2 here. So I want to break up my variables so that I have exponents that are even numbers. So that would be x to the fourth times x to the first. And the reason we like that is because now the square root of x to the fourth can come out of the radical as just x squared. So the square root of x to the fourth is x squared. And then the x to the first can't be released, so that stays underneath. So we have x squared times the square root of x. So we do them things similarly here. So the cube root of 27, you're asking yourself what times what equals 27. So you can actually just put it in your calculator. If you do math and then it's option 4, brings you up your cube root. So the cube root of 27 tells you 3. Or you can go to y equals, type in x to the third power, go to the table and find which x value goes with the y value of 27. So you can see there 27 goes with 3. So this equals 3. So if the square root of x squared equals x, well, the cube root of x to the third equals x. So with cube roots, your goal is to get the variables to have exponents that are multiples of the root. So go ahead and write that in the bubble off to the right. So pause the video, copy this down. The variables have to be broken down by multiples of whatever the root is. So since my root is 3, I want my variable to be broken down with exponents that are multiples of 3. So 7 is not a multiple of 3, but 6 is a multiple of 3. So I can rewrite this as x to the 6th power times x to the 1st power. And you just want to make sure that your exponents add up to the original. So since 6 plus 1 equals 7, I am allowed to do that. And now what I can do x to the 6th power, when I take the cube root of that, that gives me x squared. Because really x to the 6th power is x to the 3rd times x to the 3rd. And if I cube root x to the 3rd, I get x. So the cube root of the first x to the 3rd gives me x. And the cube root of the second x to the 3rd gives me x. And x times x gives me x squared. So that gets to be released because 6 was a multiple of 3. But x to the first, that 1 is not a multiple of 3, so that has to stay. It's trapped under the radical. So we have the answer of x squared times the cube root of x. Fourth roots. We have the fourth root of 81. So what times what times what times what is 81? So I can even go up to my table here. I have 81 as my third number, so that's 3 to the 4th power. So that means the fourth root of 81 equals 3. And that's because 3 times 3 times 3 times 3 equals 81. So that's 3. Well, if the square root of x squared is x, and the cube root of x cubed is x, well then the fourth root of x to the 4th is x. And then, just like the other ones, I had to get this to be a multiple of 3, and I had to get this to be a multiple of 2. I need this to be a multiple of 4 because my root is 4. So I need to figure out how to get 9 to turn into a multiple of 4. Well, 9 is not a multiple of 4, but 8 is, so I can rewrite this as x to the 8th times x to the 1st. Don't forget the fourth root there. So x to the 8th can come out because it is a multiple of 4. So the fourth root of x to the 8th is equal to x squared. All I'm doing there is dividing. 8 divided by 4 gives me 2, so that's x squared. And then the fourth root of x to the 1st, well, 1 is not a multiple of 4, so it's trapped. So this gives me x squared times the fourth root of x. And then fifth roots, the fifth root of 243. Well, you can see 243 made my list. That's 3 to the 5th power. So the fifth root of 243 is 3. The fifth root of x to the 5th is x. And then same thing with the other ones. In order to pull it out, it needs to be a multiple of 5. So in order to turn the 12 into a multiple of 5, well, our next closest multiple of 5 less than 12 is 10. So this will be x to the 10th, x squared, because remember, I need these to add up to my original, so 10 plus 2 is 12. And I needed x to the 10th because I have a fifth root, so 10 is a multiple of 5, so that gets released as x squared because 10 divided by 5 is 2. But my other guy, the 2, is not a multiple of 5, so that's trapped. So that stays. So I have an answer of x squared on the outside times the fifth root of x squared. And then we say, for the most part, you will only be asked to break down square and cube roots. So you probably won't see the fourth roots or the fifth roots. You'll probably only see square and cube. But on the off chance that they do ask you about a fourth or a fifth root, we are going over those as well. And then we have this section, what about negatives? Well, pause the video and write this down. Even number roots use I. So that's your square root, which your square root is the root with the imaginary 2 in it. It doesn't have to be there. It's implied that it's a 2. And your fourth root. And then odd roots don't use I. So your cube root, your fifth root, your seventh root, anything that's an odd number root, do not use I, which we learned about I yesterday. Remember, I is equal to the square root of -1. So copy that down, and let's look at what we get here. The cube root of -8. Well, let's put this in our calculator and see what happens. math 4, negative 8. I get an answer of negative 2. Well, let's see what happens if I do square root of a perfect square. Let's do 9 because 9 is a perfect square. Sorry, negative 9. The square root of negative 9. When I do that, I get error because you can't take the square root of a negative number. That's why we have that I. But when I did the cube root of a negative number, I didn't get an error. So that's why in that box you're writing down even roots use I, odd roots don't. Because if I have a odd number root with a negative, it's going to work. So my answer is negative 2, and that's because negative 2 times negative 2 times negative 2 does equal negative 8. Negative 2 times negative 2 is positive 4, and positive 4 times negative 2 equals negative 8. So the fifth root of negative 27, well, that's supposed to be, sorry, that's a typo. This is supposed to be the third root of negative 27. The third root of negative 27. That equals negative 3 because negative 3 times negative 3 times negative 3 equals negative 27 because this gives me positive 9 times another negative 3 gives me negative 27. And the cube root of negative 125, that equals negative 5 because negative 5 times negative 5 times negative 5, this gives me 25 positive because a negative times a negative, and then I multiply by another negative 5, I get negative 125. So the best way to figure these out is to just do a ton of practice. So the directions are simplified completely. So I went ahead and wrote these down so we can reference them quickly. So go ahead, pause the video, write this down so you can use them to help solve these problems without having to flip to another page. So number 1, cube root of 54. Since it is a cube in the radical, I need to use the cubes. 54 is not one of the numbers that are on that list, which means I have to go through the process that I was doing yesterday. I have to figure out what is the biggest perfect cube that goes into 54. So I start where I would be smaller than 54. So I'm going to not use 64 because that's too big. So 54 would fall in between 27 and 64. So I'm going to start with 27 and see, can I divide 54 by 27? So we go to our calculator, 54 divided by 27. Okay, that works. I get 2. So that means 27 times 2 is 54. So I can rewrite this problem as the cube root of 27 times 2. 27 is one of our numbers from our list. It's a perfect cube. And 27 times 2 is how I get 54. So we like this because I can take the cube root of 27 since it's a perfect cube. That's 3 times 3 times 3. So the cube root of 27 equals 3. It gets released because it's a perfect cube. But the 2 is not a perfect cube. You see, 2 is not on our list of perfect cubes. So it gets stuck underneath the radical. So the 2 is trapped, but now we have a 3 out front because the cube root of 27 was 3. So your goal is to rewrite these numbers that are under the radical using the numbers from our list up here. So 48, the fourth root. Well, 48 is not on our list of fourth roots. So I'm going to see if I can break down 48 using these numbers. So I'm going to start smaller than 48. So that would be 48's in between 16 and 81. So I'm going to start with 16. See if I can divide 48 by 16. Oops. 48 divided by 16, I get 3. So it works. So 16 is the winner here. So I can rewrite this as the fourth root of 16 times, what was it? 16 times 3. 16 times 3. We like this number because 16 is on our list. So that means it's a perfect fourth. So the fourth root of 16, if you don't know it, remember you can go math. And to get a fourth root, you're going to choose option 5. And we just need to change this to a 4. So the fourth root of 16 gives me 2. So this is 2 outside. It got released because it was a perfect fourth. But the 3 is not on our list of perfect fourths, so it gets trapped inside. So there's our answer. Number 3, the cube root of 250. So I look at my list of cubes and 250 is not on it. So I want to break it down. So we're going to see starting with the smaller than 250. So 250 falls in between 216 and 343. So working our way down, 216 definitely doesn't go into 250, but if you're just like really questioning, you can always just check. 250 divided by 216, no, you get a decimal. So it's not that. Let's move on to the next one. So the next smaller number is 125. So 250 divided by 125. 2. 125 works. So I can rewrite this as the cube root of 125 times 2. And we like the cube root of 125 because it's on our list. So the cube root of 125, well, this goes 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, so it's 5. So this gets released as a 5, but 2 is not on the list of perfect cubes, so that is trapped underneath the third root. So our answer is 5 cube root of, I wrote 5, but I meant to write 2. 5 cube root of 2. Number 4, the fifth root of 160. 160 is not on our list of perfect fifths. It would fall in between 32 and 243. So working our way down, let's see, can I divide 160 by 32? Let's check it out. 160 divided by 32. Yep, it gives us 5, so that does work. So I can rewrite this as the fifth root of 32 times 5. And again, we like 32 because it's on our list of perfect fifths. It's right here on our list of perfect fifths. So this is good. The fifth root of 32. So it's asking what times itself 5 times equals 32, and that answer is 2. And if you're not sure, again, you can type it into your calculator. So I can do math 5 to get the fifth root, and I just change that to a 5. And I type in my number, 32, and I get 2. Or I can go to y equals and type in x to the fifth power, second graph, to get all of my perfect fifths. So I can see 32 is paired up with 2. So that means the fifth root of 32 is 2. But 5 is not on our list of perfect fifths. So let's see, perfect fifths, there is no 5 on this list. So that 5 is trapped. So that stays underneath, trapped forever. All right, now let's throw in some variables. We always got to make it more complicated. The cube root of 27x to the third y. So let's break it all apart like we were doing yesterday. So the cube root of 27 times the cube root of x to the third times the cube root of y. Well, looking at my list of perfect cubes, 27's on there. 27 is a perfect cube. It's 3. So this is good to go already. X cubed is a perfect cube because it needs to be a multiple of the root, and 3 is a multiple of 3. But y to the imaginary first power, that's not a perfect cube, and I can't break it down anymore because 1 is as low as it goes. So that y is going to be trapped forever. But we can release the 27 and the x to the third. The cube root of 27 is 3. The cube root of x to the third is x. But my y is trapped. So altogether, I get 3x times the cube root of y. I'll highlight for those of you that helps. Number 6, let's break it apart. So the 4th root of 625. The 4th root of x to the 4th. And the 4th root of y to the 6th. So first up, let's see if 625 is on our list of perfect fourths. So fourths, well, I didn't get that far. So let's go to our calculator, go to y equals, and change that to x to the 4th power. And go to the table and see if 625 is on here. Okay, it is. So 625 is 5 to the 4th power. So that's good. So this is a perfect fourth. That gets released as a 5. X to the 4th is a perfect fourth because the exponent is a multiple of 4. So that gets released as x. And y to the 6th. 6 is not a multiple of 4. But what I can do is break this down as y to the 4th, y squared. Because remember, they still have to add to the original. So 4 plus 2 is 6. So that's good. And the reason why I wanted to do that is because now I can pull that out. The 4th root of y to the 4th, that's good to go. That comes out as y. And then just this y squared is all that's left underneath. So that's trapped underneath the 4th root. So on the outside, I have the 5 that got released, I have the x that got released, I had the y that got released, and then the y squared is trapped. So my final answer is 5xy and the 4th root of y squared. So 5xy and the 4th root of y squared. All right, 5th root now, so let's split it all up. The 5th root of 486, the 5th root of a to the 4th, the 5th root of b to the 7th, and the 5th root of c to the 5th. So far, only one of these is good to go. C to the 5th can come out because 5 is a multiple of the 5th root. 486, let's check our list of perfect fifths because it's the 5th root. So I'm going to go to y equals x to the 5th power and go to my table to see if 486 is on there. Okay, so it's not. We skipped from 243 to 1024. So 486 is not on there. So this needs to be broken down. So I need to figure out what is the biggest perfect fifth that goes into 486. So I'm going to have to start dividing, which I like having this written down because I can easily come back to look at some of my perfect fifths. So we are at 486, so that falls in between here. So I'm going to start with 243. Let's see if I can divide 486 by 243. So 486 divided by 243. Yeah, it gives us 2, so that works, so that's good. So I can rewrite this as 243 times 2. And we want to do that because 243 is one of our perfect fifths. So that gets to come out. The 2 is going to be trapped. So this comes out as, well, 243, the 5th root of 243. If I go back to my table, 243 is with 3. So the 5th root of 243 is 3. So that comes out as a 3. And 2 is trapped. It is trapped underneath the 5th root forever. Now let's work with our variables. Oh, and the c to the 5th, the 5th root of c to the 5th is just c. And let's look at a and b now. 4 is not a multiple of 5. And I can't break down 4 to become a multiple of 5 because 4 is smaller than 5. So there's nothing we can do. If the exponent is less than the root, then you can't do anything. It is trapped no matter what. So that comes down, it's trapped. There's nothing we can do because the exponent is smaller than the root. But we can help the b here because 7 is more than 5. So I can rewrite this as the 5th root of b to the 5th times b squared. And I got the 5 because I wanted it to be a multiple of 5, and then I got the 2 because I need it to add to 7. So now this is good. The 5th root of b to the 5th, that comes out as b. But the 2, b squared, 2 is smaller than 5. There's nothing we can do, so it's trapped underneath the 5th root forever. So we had 1b come out, we have b squared trapped, and we had this c come out. So all together, my answer, I've got 3b and c outside. And then I have 2a to the 4th and b squared trapped underneath. So my answer is 3bc times the 5th root of 2a to the 4th b squared. Number 8, so now we're throwing in some negatives here. This is a cube root. Remember, odd roots, negatives are okay. Negatives, okay. It just means that our answer is going to be negative. So I'm going to pull this apart. So the cube root of negative 24, the cube root of m, the cube root of n to the 4th, and the cube root of p to the 6th. So let's see if anything's good to go already. Well, this is good to go because 6 is a multiple of 3. So the cube root of p to the 6th is p squared. It gets released. N to the 4th, that's not good because 4 is not a multiple of 3. But 4 is bigger than 3, so I can rewrite this to break it down. So I can have n to the 3rd times n to the 1st. So they still add to 4. 3 plus 1 is 4, so that's good. And now I can pull that out. The cube root of n to the 3rd is n. It gets released. But 1 is not a multiple of 3. It's trapped forever, so that stays underneath. So we've got 2 things out so far. 1 thing's still trapped. Well, unfortunately for this m, the exponent is a 1. And 1 is not a multiple of 3, and it is not able to be broken down anymore because it's less than 3. So that m is trapped forever. Sorry, m. And then that brings us to 24. Let's check to see if 24 is on our list of perfect cubes. It is not. 24 is not on the list. 27 is, but that's not 24. So it falls here. So I'm going to start dividing by the numbers smaller than 24. So let's start with 8. So negative 24 divided by 8. We get negative 3. So that means 8 times negative 3 is negative 24. Or I'm going to write it as negative 8 times positive 3. So this is the cube root of negative 8 times positive 3. And the reason I made the 8 negative is because 8 is the perfect cube. That's 2 times 2 times 2. So the cube root of negative 8 gives me negative 2. Remember I said negatives are okay under cube roots. That just means that our answer is going to be negative. So that gets released. But 3 is not a perfect cube, so that is going to be trapped. So finally, our answer, I've got a negative 2 outside, an n outside, and p squared outside. So negative 2np squared. And then I've got 3m and n trapped. So then we have the cube root of 3mn. Number 9. The 4th roots of 1,250 m to the 5th, n squared, p to the 20th. So the 4th root of 1250, the 4th root of m to the 5th, the 4th root of n squared, and the 4th root of p to the 20th. Well, p to the 20th is good to go because 20 is a multiple of 4. But that's the only thing that we've got that is good to go. So that's going to be released. 20 divided by 4 is 5. So that's p to the 5th. So that's done. N squared is actually trapped forever because 2 is smaller than 4. So we can't break it down to save it. So it's going to stay as the 4th root of n squared. m to the 5th can be saved, though, because 5 is bigger than 4. So I can write that as 5 to the m to the 4th times m to the 1st. So this m to the 4th gets saved. The 4th root of m to the 4th is m. And the m to the 1st is trapped. So it's better than having m to the 5th trapped. Now it's just m to the 1st. And that's your goal. It's to get as much stuff out of the radical as possible. And now we're on to the number 1250. So let's see if 1250 is on our list of perfect fourths. Okay, well, I don't go that high, so let's go to our calculator. Y equals x to the 4th, second graph, 1250. Okay, I don't see 1250. We go from 625 to 1296, so we skip it. So 1250 would be less than 1296. So I'm going to start with 625 and start dividing and see if I can divide 1250 by any of these numbers that are smaller than it. So let's start with 625. So 1250 divided by 625. All right, it worked already. We got 2. So I can rewrite 1250 as 625 times 2. So this is the 4th root of 625 times 2. The 2 is trapped. It's not on our list, but 625 is a perfect fourth. If you're not sure what the 4th root of 625 is, just go back to your table and look at it. 625 is with 5, so the 4th root of 625 is 5. So that gets released. It's free. But the 2 is not on the list, so it's trapped forever. So altogether, I have a 5 on the outside, an m, and then a p to the 5th. And then trapped underneath the 4th root, I have a 2, an m, and an n squared. So our answer is 5m p to the 5th times the 4th root of 2mn squared. Number 10, let's break it apart. The cube root of negative 216, the cube root of x squared, the cube root of y to the 7th, and the cube root of z. So we have anything good already? Well, I know for sure that that's trapped because that's z to the imaginary first, and 1 is less than 3, so we can't break it down. Same thing, x squared, that's trapped because 2 is less than 3, so we can't break that down. I can break down the 7, though. I need a multiple of 3, which would be 6, so I can write this as y to the 6th times y to the 1st. So the cube root of y to the 6th, that's good to go. That can get released as y squared. But y to the 1st, 1 is too small, so it's going to be trapped underneath there. So this comes down as is, trapped forever. This comes down as is, trapped forever. So now 216, let's see, is 216 on our list of perfect cubes? And by the way, if you haven't been following along, the way I know what list I'm looking at is whatever is in the, I call this the elbow. It's the 3rd root, so I'm looking at my list of perfect cubes. And look at that, 216's right there. So this would be 6 to the 3rd power. That's 6 times 6 times 6 is 216. So the cube root of 216 is 6, but since it's a negative 216, that means that it is negative 6. Because cube roots, negatives are okay. If that was a square root, then the negative would give us an I. So we have outside, I highlighted that in the wrong color. We have outside a negative 6, a y squared, and then trapped underneath we have a cube root, an x squared, a y, and a z. So there's our answer, negative 6y squared, cube root, x squared, y, z. Number 11, the cube root of negative h to the 4th, j to the 9th, l to the 8th, k to the 6th. So This negative doesn't have a number, so I'm just going to put an imaginary 1. So the cube root of negative 1, the cube root of h to the 4th, the cube root of j to the 9th, the cube root of l to the 8th, and the cube root of k to the 6th. Well, we've got some that are good to go. 6 is a multiple of 3, 9 is a multiple of 3, and negative 1 is a perfect cube. All of them start with 1, so the cube root of 1 is just 1, but since it's negative 1. The cube root of j to the 9th is j to the 3rd. The cube root of k to the 6th is k squared, because remember, we're just dividing the exponent by the root. Now we have to break our others down. So 4 is bigger than 3, so I can break it down as h to the 3rd, h to the 1st. So then the h to the 3rd can come out. The cube root of h to the 3rd is just h. But our h to the 1st, unfortunately, the 1 is too small, so it is stuck forever. Sorry, h. And then same thing with l. We can write this as the cube root of l to the 6th times l squared. Again, we need those to add up to the original, so 6 plus 2 is 8. I can take the cube root of l to the 6th because 6 is a multiple of 3. That comes out as l squared. But the l squared that's underneath is trapped forever because 2 is not a multiple of 3. So I have an l squared on the outside and then the l squared on the inside. So all together on the outside I have negative 1. So I'm just going to put negative, and then h, and then j cubed, and then l squared, and then k squared. And trapped underneath, I have h l squared. And there's our answer. Number 12. Let's break it all up. This is a square root. So that 2 being there is a square root, but if this problem didn't have the 2 there, and it just looks like that, you have to know that that is a square root. So the square root of 75, the square root of n to the 5th, the square root of p to the 8th, and the square root of q. So we want our exponents to be multiples of 2. That's only your exponents. We don't want our numbers to be multiples of 2. We need our numbers to be perfect squares, which 75 is not. P to the 8th is good to go because 8 is a multiple of 2. So remember, this could have the imaginary 2 there, so I'm dividing. 8 divided by 2 is 4, so that's p to the 4th. Q is trapped because this is an imaginary 1 as the exponent, and there's an imaginary 2 in the elbow as the root. So 1 is less than 2, so it can't come out at all. So that is trapped forever. 5 can be saved. Just have to rewrite it as n to the 4th, n to the 1st. Because 4 is a multiple of 2, and then 4 plus 1 is 5. So the n to the 4th gets released. The square root of n to the 4th is n squared, but the n to the 1st is trapped. And finally, 75 is not a perfect square. If I go up to my list, 75 would be in between 64 and 81. Hopefully you know that a number that ends in 5 can only be divided by a number that ends in 5. So the only option here is 25. So 75 divided by 25 is 3. So I can rewrite this as the square root of 25 times 3. And that's good because 25 is a perfect square. That comes out as a 5. But 3 is not a perfect square, so it is trapped. So altogether, this gives me 5n squared p to the 4th and the cube root of 3nq. And then number 13, 4th root of 162, 4th root of c to the 4th, 4th root of d to the 6th, and 4th root of e to the 12th. I've got a few good things. 12 is a multiple of 4, and 4 is a multiple of 4. So this gets released right away. The 4th root of c to the 4th is c. The fourth root of e to the 12th is e to the third, because again, we are just dividing 12 over 3. D to the 6th, well, 6 is not a perfect fourth. It's not a multiple of 4, but I can break it down and make this say d to the 4th, d squared, because 2 and 4 give me 6. And then the fourth root of d to the 4th comes out as d, but the fourth root of d squared doesn't work, so that's trapped forever. And then we just have to figure out 162. So let's see if 162 is on our list of perfect fourths. And I know it's fourths because it's the 4 in the root. So fourths, 162 is not on the list. 162 would fall in between 32 and 243. So let's see if I can divide it by 32. If not, then we're kind of trapped. So 162 divided by 32. Oh, wait, wait. What am I missing? Sorry, I was looking at the list of fifths. My bad. I would start with 81. Try dividing it by 81. So 162 divided by 81. It does work. It gives me 2. So I can rewrite this as the fourth root of 81 times 2. And that's good because 81 is a perfect fourth. So that gets released. The fourth root of 81, well, we can see 81 to what times what times what times what equals 81. So I can do math 5, change that to a fourth root, and say 81. Nope, not 48. 81. And we get 3, or I could go y equals x to the 4th, go to my table, find 81, and see that it's with 3. So this gives me a 3 outside, but 2 is not a perfect fourth, so the 2 is trapped. So on the outside, I get 3c d e to the 3rd. And underneath, I get 2d squared. Okay, we got 6 more questions, 1 more page. Simplifying radicals with fractions. So we do this the same way here. We're just going to have a 1/2 out front, which I'm just going to highlight as something that's on the outside. That's going to stay on the outside until the very end of the answer. So we're going to just do this how we have been doing it. So the cube root of 16, the cube root of f to the 3rd, the cube root of g, and the cube root of h to the 5th. My cube root of f to the 3rd is good to go because that's a multiple of 3, but that's the only one. So that gets released as an f. G is trapped because 1, the imaginary 1, that's less than 3, so I'm not going to be able to break that down. 5, I can break that down, so I can rewrite this as h cubed, h squared, because again, I need those to add up. So 3 plus 2 is 5, and we wanted the 3 because now I can take the cube root of it. The cube root of h to the 3rd is h. H squared is trapped, though, because 2 is less than 3. So that's trapped. The h is out. So now I just need to look at 16. So let's see. Is 16 on the list of perfect cubes? So I go to cubes. 16 is not on the list of perfect cubes. It would fall right here. So I'm going to start with 8. Hopefully you know that 16 divided by 8 is 2. So I can rewrite this as the cube root of 8 times 2. And we like that because 8 is a perfect cube. 2 times 2 times 2 is 8, so this gives me a 2. But the 2 that's underneath is not a perfect cube, so it's trapped. So altogether, we get 2 f h cube root of 2g h squared. But remember, I have that 1/2 from the beginning, so it's 1/2 times that, which if I do 1/2 times 2, I just get 1, 1/2 times 2 is 1. They just kind of cancel each other out. So I'm left with FH times the cube root of 2GH squared. Number 15. So I have a negative 3 over 5 out front. So I'm going to bring that down so I don't forget it. And then let's break this down. So the cube root of 250, the cube root of f to the third, the cube root of g, the cube root of h to the fifth. Well, here, that's good. That's a multiple of 3. So that comes out as f. This is trapped because imaginary 1 is less than 3, so that's going to stay. So we've got some of this done already. H to the fifth, I have to break that down. So h squared, h to the third, h squared. So now the h to the third can come out. The cube root of h to the third is h, but the h squared is trapped. And then 250. Let's see if 250 is on our list of perfect cubes. It is not, so I would start dividing. 250 can't be divided by 216, but it can be divided by 125. 250 divided by 125 is 2. So I'm going to rewrite this as the cube root of 125 times 2. And this is good because it's a perfect cube. So the cube root of 125, if I go x to the third power, go find 125, I can see the cube root of 125 is 5. So this comes out as a 5. And the 2 is trapped. So all together I get, I have the negative 3 over 5 and the 5 on the outside, which if I multiply negative 3 over 5 times 5, well, hopefully you know that those 5s eliminate, but if you don't, just use your calculator. Negative 3 over 5 times 5, and I get negative 3. So that gives me negative 3. Then I have an f on the outside and an h on the outside. And then underneath the cube root, I'm left with a 2, a g, and an h squared. Four more questions. 2/9 times the cube root of 54r to the 6th t to the 8th. So we have this 2/9 out front that I'm just going to bring down. The cube root of 54, the cube root of r to the 6th, and cube root of t to the 8th. R to the 6th is already good because 6 is a multiple of 3, so that comes out as r squared. T to the 8th is not because 8 is not a multiple of 3, but I can rewrite that as t to the 6th t squared because 6 plus 2 is 8. And now I can do t to the 6th. The cube root of that is t squared. But I cannot do the cube root of t squared because 2 is less than 3, so that's trapped. And now I just look at 54. 54, is it on my list of perfect cubes? No, it is not, so let's start dividing. So it would fall here, so I'm going to start with 27. 54 divided by 27, you see that it gives you 2. So I can rewrite 54 as 27 times 2. So this is the cube root of 27 times 2. And the 27 is a perfect cube. It's 3 times 3 times 3, so that comes out as a 3. But 2 is not a perfect cube, so that is trapped. So that stays underneath, so that's the cube root of 2. Now I have the 2/9 out front, so 2/9 times 3. Well, I can reduce this. The 3 and the 9 can be reduced because this is a 3 and this would become a 1. So this gives me 2 times 1, which is 2 over 3. If that math is too much in your past, multiplying fractions, you can just do 2 divided by 9 and then multiply it by 3. You get a decimal, so hit math and then click fraction and hit enter and it will make it a fraction for you. So 2/3. Also on the outside I have r squared and t squared, and then I'm left with the cube root of 2t squared, giving us that as our answer. Number 17, just like yesterday, we can separate our numerators and our denominators, but first thing you're going to want to do is see if you can simplify underneath. So I can actually do 160 divided by 10. 160 divided by 10 just gives me 16. And I can do f to the 8th divided by f squared, because remember, when you divide, you subtract your exponents. So 8 minus 2 is 6, so that's f to the 6th. G divided by g, those just cancel each other out because they're the same thing. And then h to the 5th divided by h squared. Subtract your exponents, that gives you h to the 3rd. So after I simplified that, I don't even have any fraction anymore. So this is just the cube root of 16f to the 6th h cubed. So now I can pull this apart. So this is the cube root of 16, the cube root of f to the 6th, and the cube root of h to the 3rd. This is good, and this is good, because they're multiples of 3. So that's f squared on the outside, and that's h on the outside. Those were released, but 16 is not a perfect cube. If I go to my list, 16 is not on the cubes list. So I'm going to have to start. 16 would be here, so I start dividing, and yes, 16 can be divided by 8. 16 divided by 8 is 2, so this gets rewritten as the cube root of 8 times 2, and then the cube root of 8 gets released as a 2 because 2 times 2 times 2 is 8. But the 2 is trapped, so that stays underneath, giving me an answer of 2f squared h, and then the cube root of 2. Number 18, let's see if I can simplify anything before I separate. So d squared and d to the 10th. Well, this can be eliminated, and this can become an 8. And then f to the 5th and f to the 1st. Well, that can get eliminated, and this can switch to a 4. That's all I can do, so I do have to have a fraction still, so I'm just going to pull this all apart. The cube root of 8, the cube root of g, the cube root of h, and the cube root of f to the 4th now, divided by the cube root of 27, and the cube root of d, and now that's the 8th power, and the cube root of e to the 7th. We've got a few things that are good to go. 8 is a perfect cube, 27 is a perfect cube. G and h, those imaginary ones for exponents are too small to be taken care of, so those are trapped. So I can pull those all down already. The cube root of 8 is 2. The cube root of 27 is 3, so that's good. We are left with a cube root of g and a cube root of h. But now I can break down the f to the 4th power. I need it to be a multiple of 3, so I'm going to write that as the cube root of f cubed f to the 1st. So now this can get released, but f to the 1st is stuck. These are stuck. These are released already. D to the 8th, I can rewrite that as d to the 6th, d squared, because 6 is a multiple of 3. So that'll get released, but d squared is trapped. And then e to the 7th, I can rewrite that as e to the 6th, e to the 1st, because remember, 6 plus 1, it has to add to the original. So that's 7. And 6 is a multiple of 3, so that gets released, but this e is trapped. So this leaves me with 2, the cube root of g, the cube root of h. Then the cube root of f cubed gets released, but the f to the 1st is trapped. And then on the bottom, I've got the cube root of d to the 6th. That comes out as d squared, but the other d squared is still trapped. And the cube root of e to the 6th is e squared, but e to the 1st is still trapped. So all together, on my outside, I have on top 2f. On the inside, I have the cube root of GHF. And then on the denominator, on the outside, I have 3d squared e squared. And underneath the radical, I'm still having a 2d and an e trapped. So we have our answer of 2f cube root of GHF over 3d squared e squared cube root of d squared e. And finally, our last question. Let's see if I can simplify anything before we go. X to the 9th divided by x to the 3rd. Well, those 3 on bottom can cancel with 3 on top, leaving me 6. And y to the 6th divided by y to the 1st. That 1 on bottom can cancel with 1 on top, leaving me with y to the 5th. So I have the cube root of 81, the cube root of x to the 6th, the cube root of y to the 5th, divided by the cube root of 125. So I get 81 is not a perfect cube. It's not on my list of perfect cubes. But it can be divided by 27, which is on my list of perfect cubes. So that can actually be written as 27 times 3. Cube root of x to the 6th is good to go already. That comes out as x squared. And y to the 5th, that needs to be broken down because 5 is not a multiple of 3, so I can say that's y cubed y squared. And the cube root of 125 is already good to go because 5 times 5 times 5 is 125, so that is already released. So now I can pull the cube root of y cubed out, and I can pull the cube root of 27 out. The cube root of 27 is 3, and then the 3 is trapped. I've got the x squared on the outside. The cube root of y cubed is y, and then the y squared is trapped over 5. So finally, on my outside, I've got 3x squared y, and then the 5 on bottom, and I've got inside 3 and y squared. So I get 3x squared y, cube root of 3y squared over 5. And there you go.